Hello, my name is Jana Blum. Welcome back to our video as we continue our series on Lewis structures. In this video, we'll be talking about formal charge and using formal charge to evaluate non-equivalent resonance structures. First, let's remind ourselves on what is resonance and what does it mean to have an equivalent resonance structure. Resonance occurs when I can draw a molecule or a Lewis structure in more than one way and satisfy all the electron needs in terms of the octet rule or the full valence. So an example would be the NO3 or nitrate ion. I can draw three different resonance structures. We can call them A, B, and C. And the only difference between these three structures is where I'm placing the double bond. But you'll notice each bond, each structure has a nitrogen single bonded to two oxygens and a double bond to the other. So if I look at structure A, we can see I'm just kind of moving the position of the double bond in structure A, in structure B, and in structure C. And this is what we call equivalent, because really the true structure, that electron pair that we're looking at here that's in the double bond, that electron pair is distributed, is delocalized across all three of the oxygens. But we can't represent that in drawing, and so we use the double arrow to show us that it's somewhere in between those three structures. And we consider that to be an equivalent resonance structure. Now, if we look at the resonance structure for the cyanate ion, OCN, I drew three Lewis structures for this ion, with C being central. And carbon is central because it is the least electronegative here. And in this case, these are what we call non-equivalent structures. These are non-equivalent. Because when I look at structure A, I have a single bond to oxygen and a triple bond to nitrogen. Structure B has a double bond to oxygen and a double bond to nitrogen. And then lastly, structure C has a triple bond to oxygen and a single bond to nitrogen. So these, unlike the previous example, these are distinctly different resonance structures. And when we have non-equivalent resonance structures, as in the equivalent ones, we said that it was somewhere in between those three. In non-equivalent, one of the structures may be preferred, and we can use formal charge to determine which is the preferred structure. So what is formal charge? And we're going to do an example of this using the structure A for the cyanate ion. So formal charge is defined by each individual atom in my structure. And it is defined as the number of valence electrons on the atom minus the number of bonds to attach to that atom minus the number of lone electrons. So what essentially this is telling me is if the number of valence electrons minus the bonds, minus the lone pairs is 0, then oxygen has the same amount of electrons on it that it did in its native state. If I have a formal charge of negative, it means it has one extra electron, and if it has a formal charge that's positive, it means it's one less electron than in its neutral state. So we can calculate the formal charge for each atom in our substance. So if we look at the oxygen atom in the Lewis structure above, oxygen has, so we'll just do formal charge. The formal charge of this oxygen atom is 6 valence minus the number of bonds, because in a bond I have 2 electrons, so the oxygen is essentially seeing half of that. So if we just count the number of bonds on that oxygen only, that's 1 bond, minus the lone electrons that oxygen sees is 6. Don't count lone pairs. We're counting each individual electron here, so there's 6. And that gives oxygen a formal charge of -1. Again, it just means if I'm looking here at oxygen, oxygen has 6 electrons here. Lone electrons belong solely to the atom, and then it has 1 electron out of that bond. And so this oxygen essentially sees 7 electrons that belong to it. Because it only has 6 in the valence, it has 1 extra electron. And so that is why it has a formal charge of -1. And whenever we calculate non-zero formal charges, we like to put them in the Lewis structure of -1. Now we can look at carbon. Carbon here has 4 valence electrons, and again, I know that from the periodic table, minus the number of bonds, so carbon has 4 bonds, and nitrogen has, carbon has no lone pairs, no lone electrons on it, so the formal charge on carbon is 0, and then lastly, nitrogen has a formal charge of 5 valence electrons minus 3 bonds minus 2 electrons, and so it has a formal charge of 0. And so that works out well. The sum of the formal charges has to equal the charge on the atom or the molecule or the ion. So because this is a polyatomic ion, and it has a charge of -1, the sum of the formal charges has to equal -1. And that holds because the only formal charge I have is on oxygen. We can do this formal charge analysis for our other molecules. So if we go back to our 3 equivalent ones, we can put our formal charge here. So my formal charge was on oxygen here, and then the carbon and nitrogen were both 0. If I look at structure B, the formal charge of oxygen, again, 6 valence, minus 2 bonds, minus 4 lone electrons is 0 on that oxygen. Carbon is still 4 minus 4, no lone pairs, still 0. And then the nitrogen here is 5 minus 2 minus 4. And so the nitrogen has the -1 charge on it. And then lastly, my formal charge, and again that does add up to -1, so that's good. And then I can do my last structure here. Now oxygen is going to be 6 minus 3 minus 2. So now oxygen has a +1 charge. Carbon is still 0. And then my nitrogen is 5 minus 1 minus 6, which is a negative 2 charge. And so in this case, they still do all add up to minus 1. So now we need to decide which is the best of these three structures. So who's best? So I'm going to erase this. Sorry, I'm going to erase this text. So the best structure is the one where any negative formal charges should be on the most electronegative atom. Or closest to 0. Formal charges 2 or greater tend not to exist. They don't tend to be very stable. So if I compare electronegativity values and looking at the periodic table, oxygen is more electronegative than nitrogen. So structure A is the best structure. That meets these requirements. I know I have to have some formal charge on this atom because I have a net charge on my substance. So if I'm going to have a negative charge, I'm going to want to have that negative charge sitting on my oxygen. In the structure here, I have a positive charge on oxygen, and oxygen is very electronegative. It does not want to lose or give up any of its electrons, and so that's a highly unlikely structure to exist. And then nitrogen is not quite as electronegative as oxygen, so oxygen is more likely to hold on to those electrons. So that concludes my video on formal charge. Thank you.